The most rush is the season. What do you mean there's more fillers? There was an episode that was a filler. It's like telling a backstory on a damn boring. Suddenly cutting up with that's a filler. I think that's more something. Yeah, they have nothing to do with the law at all. What has nothing to do with the law? What's the backstory? Actually, big chili, bro. Is it finishing this season? Yes, last season. I grew up with I'll probably die with it.
Take your answers.
Everyone was like, oh, I'm back alive. It's so cool. It's not so much like the second season. No, it was just depressed because no, it's not gonna end. It's depressed because all the shit is happening in the Marley and Perry. I didn't see anything. Everything I think Marley and Perry. How do you feel about AMD getting perfect origin? Deserve. It's not yet like production value. Right? They should. So sad, the androgenized medium. That's Chad. Best film. Best boy. You know, he used to be that way. Before the first appearance of the fact that was dying. Yeah. No.
So let's start. So we finish off the magnetic field. Okay, so as usual, recap. So what do you learn so far in magnetic field? Equations. First, F equals to current carrying conductor, magnetic force. What formula? F equals to V IL sin theta. F. A charged particle move in magnetic field. What is the force? What formula? F equals to V QV sin theta. Okay. Second equation for force experienced by a charged particle. First equation for a conductor. Okay. Then recently, before that, we talk about any charged particle move in magnetic field takes what path? Makes a circular path. What is the condition to make a circular path? The force must be perpendicular to the direction of motion of the particle. So then we end up investigating about the radius and everything. What force equals to what force will lead you to get the radius? The magnetic force equals to the centripetal force. You get the PQV equals to what? MV squared over R. We can able to find the radius of the circle. Okay. Now recently we talked about what? Last class we discussed about Hall effect. Okay. Hall effect. What is Hall effect? When a magnetic field is applied to a thin sliced semiconductor, the electron will deflect to one edge, create a electric field, and result to a Hall voltage. Okay. The Hall voltage is very small or huge. Normally, it's very small. Okay. So the direction of the electric field, where's the magnetic field, and everything you have to know. And finally, the Hall voltage proportional to what? The whole voltage proportional to what? The strength of the magnetic field. More stronger the magnetic field, more greater the Hall voltage. Okay. So why we use semiconductor better than conductor as a hot probe? Why we use semiconductor is better material than the conductor to act as a hot probe? Because the Hall voltage found to be inversely proportional to charge density. Okay. So therefore, we use semiconductor to get a significant Hall voltage. Okay. Why use a thin slice? Not a thick one. Why use a thin slice as a Hall probe? The plate must be very thin. Why? Again, the Hall voltage is inversely proportional to the thickness of the plate. Okay. So this all will be asked in exam like one full structure. You have to know. Okay. Okay. So recently we talk about velocity selector. Right? Yes. Yeah, so this is another main thing they're going to ask in exam. I told you yesterday. Electric field and magnetic field is enough to find what is the speed the charge particle move into the velocity selector. Okay, so V over B. Okay, to get the velocity. Okay. So how they got V over B? As I said, the magnetic force must be equal to the electric force, and then the charge particle move straight. Okay, this also can be a one full structure. Okay. They will tell you the magnetic fields applied inward. Okay, where which plate should be positive, which plate should be negative. Okay, which is the magnetic force direction, where's the electric force direction, and finally what is the velocity. And this, okay, like one full structure. Okay, instead of cross into the page, they might apply the magnetic field out of the page. So it's going to be a dot. It's going to be a dot. So magnetic field out of the page, then how the electric field should be? The positive plate must be the down plate, right? Down plate will be the positive plate. But whatever it is, the electric field and magnetic field must be such a way that what should be always in opposite direction? The magnetic force and electric force must be always in opposite direction. Okay. Maybe the next step we have to devise this velocity selector can show in the lab. How it goes. So now, this velocity selector, main one, V equals what? E over B. Okay, then I also tell you about mass spectrometer. Okay, although this use mass spectrometer actually for physics, what do you call, in terms of physics, mass spectrometer, in terms of chemistry, say, you find isotopes. But instead of physics, mass spectrometer is used to find specific charge. Okay, specific charge. E over M, call it specific charge. Charge per unit mass. Specific charge. All three isotopes will have a different. Let's say you have three isotopes in this source. All three will have a different specific charge. What is it? All three of them have the same charge, but have a different mass. Therefore, will have a different specific charge. Okay. So, as I said, first we apply magnetic field, electric field to identify what velocity is traveling. Okay. Then we come to the second region. All will make a different radius because we apply magnetic field alone only. So make a different radius. The most massive will take a big radius or smaller one. Massive particle will take a big radius or a smaller radius. Big radius. So more massive will be make a bigger radius. Okay. So from here, how they found the specific charge. Okay. Another list of formulas. Okay. These are the four formulas. Okay. The main one in your syllabus currently is second one and the first one. Okay. This one they never really emphasize now, but good to know. Okay. Never trust Cambridge, as I told you. Okay. Okay, so velocity selector V is E over B. Okay. But the velocity, there is another way to find the velocity too. By using the electron gun itself. Okay. You can find the velocity of the charge by two ways. Okay. In exam 10 times they ask what is the velocity, 9 times velocity selector, once they ask like this, what is the velocity selector by using the electron gun. Okay. So electron gun, as I told you, is in the CRO. Okay. In the CRO, here, spectrometer. It is apply a potential difference here. Okay. So the potential difference, the electron which is after out of the plate, free from the plate, the potential difference pull the electron. So what happened? It's electric field. So the electron accelerated due to electric field. So what happened? What type of energy change? What type of energy for the electron? And pulled by the electric field. So the kinetic energy, the work done by the electric field, EV. Work done by the electric field, EV, right? Remember AS, QE is the work done. Work done by the electric field is equal to gain in kinetic energy of the electron. Electron gain kinetic energy. So half mv squared equals to EV, and the V difference, this V is velocity, the other V is the potential difference in the electron gun, will give you the velocity of the charge particle. Okay. So two ways we can find speed of the charge particle. One by using the electron gun itself, if the voltage of the electron gun is given, the work done by the electric field is equal to gain in kinetic energy. Or velocity selector, which is very famous. EOB is your velocity of the charge particle comes out. Okay. So we can calculate the V by using the EOB. And then finally, what is the purpose of this mass spectrometer in the physics perspective is charge per unit mass as specific charge. So we got this region, they are able to find the radius by using the alpha wave, the strike rule. Okay, isotope. You can find the radius here. So because here only magnetic field is applied, so and it's making a circle, so centripetal force must be equal to the magnetic force in the second region. Okay, so centripetal force mv square of r v2 ev right? v2 second region is magnetic field strength. Okay, so then from there you want to find specific charge E over m. So make the E over m the subject. This is the formula V over v2r. So V2, we can calculate, we know how much the V2 magnetic field strength they applied here, how many Tesla. R, you get it from the photographic plate. Then V, you have to look upward for the velocity, from the velocity selector we get the V. Okay, we can find the specific charge. Okay, so this mechanism, you have to know, especially the first two. Okay. Okay, and the second one mainly. This current syllabus, they really highlighted the velocity selector. Okay, is missing. The first one is normally they never really highlighted, but always they ask. Okay, but they really highlighted the velocity selector. Okay, E over B. Any questions about this setting? Okay. Okay, so let's move on. Okay, the last part of this topic is force between conductor. When you have two wires carrying a current, they will experience a magnetic force. Okay, you learned this before, right? Okay, so if the current, the two wires carry the current in the same direction, it repel or attract? Repel. Okay. So current in the same direction, it will repel. Attract, right? It will attract. So current in the same direction will attract, opposite direction, wires will be repelled. Okay. So the parallel conductor carries the current in the same direction, experience an attractive force, and the other one is a repelling force. Okay, why the current carrying the same direction attractive in nature? What's the reason you learn in your early studies? Same direction, use a right hand rule, the field right. Okay, the field up. So the field in between, opposite each other, right, at the center. The field cancels. So the field at the side is stronger. It attracts. Okay. But this explanation is not accepted now. Okay. A levels, they want you to explain in terms of Newton's third law. Okay. So how Newton's third law links to this? Okay. Explanation. So that's what we're going to do now. Okay. Okay, so we're going to explain why it attracts. Okay. So for that, let me go to the paint. Okay, so we discuss all effects. So the mass spectrometer. And now here, force between current carrying conductor. Pictures to. So we follow this description here to draw the diagram. Okay. So what are we going to do now? How to explain why the two wires carrying current attract by using Newton's third law. Okay. So look at the first point. Consider two wires A and B carrying a current IA, IB flowing out of the plane of the paper. Okay. Let's say you have two wires. Okay, it's a plane view. So coming out of the paper, you put a dot across. So the dot, right? Two wires, plane view, A and B. A and B carries current out of the page, out of the paper, out of the plane. Okay. So we know these two wires are attractive in nature, right? So we're going to explain why. Okay, by using, follow this statement. By using right-hand grip rule for figure A, so let's say this is the first A. For figure A, we find that the magnetic field due to current IA, so the current at A is IA, the current B is IB. Okay, by using the right-hand grip rule, we find that the magnetic field due to IA at the position of B is directed upwards. Do you agree? The second line. They asked in one structured question. Which direction? Try to understand the second word. By using the right-hand grip rule, use your right-hand grip rule at figure A. So this is your figure A. Okay. So we find that the magnetic field due to IA, at B is upwards. The wire B experience force due to its own field or its the neighbor's field, the other wire's field, neighbor one, right? Do any body experience force due to its own field? No, it affects others, right? So the magnetic field which effect force on B is magnetic field of A, right? So magnetic field of A at B, which direction? How the magnetic field at A looks like? Current is coming out of the page. How the field looks like? Right hand grip rule, right? So use right hand grip rule. How the field here looks like? Clockwise, anti-clockwise? Anti-clockwise. Please, anti-clockwise. So at this point, the field of A is straight. Yeah. So the field of A at B is upwards. Okay. So that field we label it as B of A. B of A. Okay, B of A. So the wire B experience affected by magnetic field of A, which at B acting upwards. This is a 1 mark question in the structured question. 1 mark. Which direction magnetic field of A at B is right hand grip rule. Okay. Let me test. What is the magnetic field of B at A? Upwards, downwards. Right? The magnetic field of B at A is downwards. Okay. We focus to B first. Okay, so that's the second line. By using the right hand grip rule, figure A, find the magnetic field of IA at position B is BA directed upwards. Okay, look at the third one. Okay, now can you identify the third point? Rick, do you understand what I'm trying to explain? By using Fleming left hand rule, can you find the direction of the force experienced by the B? By using Fleming left hand rule. The B experiences a magnetic force, magnetic field upwards, and the B carries a current out of the page. Therefore, it experiences force which direction? To the left. The left, right? Yeah. By using Fleming left hand rule, the force acting on the wire B towards the left, right? Towards the left. Okay. So by using Fleming left hand rule, we found that the force experienced by the B is towards the left. This is the force experienced by B. To the left. Okay, now if I ask you to calculate the force experienced by the B to the left, what is the magnitude? What formula do you use? What formula to find the force for the current carrying conductor? BIL or BQE? BIL, right? BIL. Okay, now PIL. PIL. So the force at B, the force magnitude we use BIL. Okay, now be careful. Which B? B of A or B of B?
B of A.
B of A. Remember, magnetic field of the other body. I of what? I of A or I of B? I of B. L? L of A or L of B? Which L? Oh, okay. L is little confusing. You see, if you have two wires, one short, one long, okay, this is your wire A, wire B, side view, okay. The length you're supposed to use is which length? The shortest length, okay. Actually, the length must use the shortest length between the A and B. Okay, BIL, the L is what? The length of the wire which is within the back end. Okay. So one short, one long, use the shorter length. Okay. Okay, but anyway, focus is force on B is magnetic field of A. Okay. I of the B. Force at A, BIL. So which B? B of B, I of A. L is the shortest length. Okay, so that's what described here, down here, the third line. FB is BA, IB, L. Here we just put L because normally in the description, the both length of the wire is the same. Okay, L. Okay. Okay, let's say question asks, your best you are, let's say you are unfortunate, they give two wires different length, use the shorter one. Okay. Yeah. So in figure B, that's your FB, to the left. So in figure B, the FA is directed towards the right. Okay. So that is BBIAL. Okay. So this FA, so FA is where? FA is to the right. In exam, they'll ask you to reason why the FA is to the right. If FB is to the left, why FA is to the right? They ask you to explain based on Newton's third law. So what is it? FA and FB is action reaction path. It's action reaction path. Okay. So what is Newton's third law stated? Every action there is an equal and opposite reaction, same magnitude but different direction, right? So you see, if FB because it's to the left, FB must be to the right. Reason why? Because it's an action reaction path. Based on Newton's third law, the direction must be opposite to each other. Therefore, FA must be to the right. Okay. If they ask reason why you choose to the right, so you blame to the Newton's third law. It's action reaction pair. Therefore, both must be opposite direction. So FA must be to the right because FB is to the left. Okay. So explanation whether it's attractive or repulsive. Now you have to go based on Newton's third law. Okay, Newton's third law. The first force you get it by using Fleming left-hand rule. The second force you have to predict by using Newton's third law. Okay. Any questions so far? So the FA or L, FB or L are the same but directed opposite each other. They constitute action reaction pair. It's the action reaction pair. This is the highlight. Highlight something new for you. Not to say something new. This is the origin of the explanation. Why the two wires carry current in the same direction and track. You have to use Newton's law. Okay. Don't ever go and explain the field between is cancelling, therefore field at the side stronger, so there is a force inward, so they attract. Not accepted. Okay? Newton's law. Okay? So you explain the first wire, but they're not going to ask you one full paragraph essay. They're going to guide you one by one in structured question. Okay? We have one after this, we'll show that. Okay, the wire carries a current in the same direction, there will be attraction of each other. The wires carrying current in opposite direction, there will be a repulsion of each other. Okay, one past year came up. This is one past year question came up. Okay, let's see how well. So 1 year came out like this. They showed two wires, same direction. They show the plane wave, the two wires current outside. They label it as Q and Y. Okay, so now the question they ask is this. So it's a how many marks? It's a 7 marks question. Give it time. So let's go to the first one. Figure 6.2, draw arrow in each case. Okay, go to the diagram part by part. Go to A first. Look at A. So draw arrow in each case to show the direction of the magnetic field at Q due to the wire of XY. Which direction? Draw and label the arrow as B. Magnetic field of what? Magnetic field at Q caused by XY. So you write in grid blue, you use for Y, right? And then you put for I, the current is coming out. The magnetic field is anti-clockwise. Okay. So here the field is downwards. The field should be downwards. So the Q you have suppose draw an arrow downwards, and this is B, right? Okay. Okay, next. Yeah. Because the Q is affected by the field of Y, right? Field of Y at Q which direction? How the field, magnetic field of Y looks like? Right hand grid blue, right? So like this, right? See? So when you come to Q, see? Downward. Because the field is circle, right? Then come to Q, the field is downwards, right?
So the one on the right hand side is always going upwards.
Sorry?
The one on the right hand side is always going upwards.
Yeah, here the field should be upward. Here downward, right? But the pattern must be, imagination is a anti-clockwise circular pattern, right? Magnetic field. Okay. So here the field is downward. Okay. So next, 2. The force at Q as a result of the magnetic field due to the current in wire XY. Which direction? 2. The force at Q due to the current in XY. Which direction? Force at Q results of the magnetic field due to current in XY. Label that force at that. Come on. Which direction the force experienced by the Q?
To the right.
To the right. To the right? Running left hand rule, right? FBI. FBI. So I coming out of the page. Okay. And magnetic field is where? Magnetic field is downwards. Okay. Only turn downwards. So your thumb point to the right. Correct? So where's your force? Force is to the right. Okay. So these are 2 marks. Okay. So we done with A. B. State Newton's third law, no problem. Every action there is an equal and opposite direction. Same magnitude but in opposite direction. So recall back Newton's third law. Okay, then use this law in A2. Use this law in A2 to state the direction of force on XY. So they just said state, they never asked you to explain. Okay. So state force on Y is to the left. Because it's an action direction. The question asks state and explain why the force is such that. So what do you say? The force should be to the left because these 2 forces are action, reaction, back. So must be opposite directions. Okay. So therefore it should be to the left. Okay. So you give reason is based on Newton's third law. Okay. So until here makes sense for magnetic field. Cambridge, as you said, you go. I don't know how many of you went through the past year questions there. Towards the end will be like something like comment. Try your what do you call your general knowledge. So the same question has been asked. So 4 marks question. General knowledge. How do you think? 4 marks. Okay, 2 minutes for you. Magnetic flux density is G from straight wire. Is this equation? This is the field strength. The field strength extended by the wire about T distance away. Okay. This wire T distance away. Okay. Okay. So use this expression to explain why under normal circumstances the wire carrying alternating current are not seen to vibrate. Make reasonable estimates of the magnitude of the quantities involved. Make reasonable estimates. It means you must tell some values for the I and D maybe. Okay. See, all the currents carried here, PNP gives us what type of current? Alternating current. Okay, we're getting all our alternating current. Only depends when you go to the laptop, it changes to direct current, so we have a diode for that. Okay. Some light bulbs all alternating current, so fine without diode. So alternating currents flowing in lots of wires. Here I think you go on top here got lots of wires all carrying alternating current. Alternating current, the direction of the current sometimes can flow in opposite direction, sometimes same direction. So the current flows same direction, it attracts, right? And when the current flows in opposite direction, they will repel. So what is the frequency of the AC supplied by the TNT? 50 Hz, around 50 Hz. So that means 50 times the force is attracted and repelled, right? So what should happen to the wire? Should oscillate, right? Attract, repel. That seems to be not observed. There is no oscillation. You're asking why? Form why it seems to be not oscillating? We don't worry about the oscillation.
Is it because the current is so low?
Current is too low. Okay, so you have to do an estimation. How much current flows in a wire and this building? Any general knowledge? 10, yeah. So you can see that. That's it's about 20 ampere, right? 50 to 20 ampere. The estimation I is from 13 to 20 ampere accepted. So I is okay. We go for 15 ampere. Okay. D.
10 years, less than 2
One wire to another wire. How much do you think the separation could be up here? Few centimeters, few meters, few centimeters, right? Maybe let's say 10 centimeter. Also very further apart. So I is 15 ampere. D is 10 centimeter. So then how do you make it very easy? Why it never oscillates?
15 divided by.
So you calculate out. So your B going to be very small or very huge?
Very small.
B is very small. Therefore,
the vibration is like so small that it's not relevant.
why the vibration is so small? Because B is small. Why vibration is so small?
The magnetic flux density is important.
Magnetic flux density is B. Okay. Why is it therefore not vibrating? The intermediate reasoning. Of course, my answer is
The
not
force
vibrating.
between the wires is low.
Force between wires is low because F equals to BIL. Okay. So because the magnetic field is so weak, so the force, the attractive and repulsive force is very low relative to what? You see, if you have a very small charge particle, you have very small force also, it can vibrate. But here the wire is not vibrating. Of course, you say the magnetic force is small. Relative to what? If it's very light, it will vibrate. But the wire is quite reasonably heavy, right? So what you can see, the magnetic force is very small relative to the weight of the wire. Magnetic force is small relative to the weight of the wire, therefore unable to vibrate. 4 marks. Okay, and here they ask. Majority of the students miss the 2 marks or 2 or 3 marks. Okay. It's just here. This is the answer. This answer is suggest a reasonable value of I and D 1 mark. Okay. So I is 15 to 20 ampere, D is 10 centimeters. Mention the expression of F equals to BIL. Okay. The force, magnetic force is BIL. So force between wires are small compared to weight of the wire. Come on. I think most probably the student get 1 mark by expressing F equals to BIL. Okay. Real examination and the examiner mark, they follow strictly with this mark scheme. Okay. They also have some extra solution at the side, except okay. Hopefully, you never mention BIL also given mark. Okay. If it's not there, this one they will still equal. Okay. Okay. So that's about one question about 2 wires carrying current. How it attract? Is it repelled? So this is how the question going to be. One full structure. Okay. So last part of the topic. Okay. So now your turn.
Okay, regarding the general volume track, usually
you have like a list for all the general knowledge, just like the typical amount of current entering or the distance between the gradient. Is there a list for it? Or you just have to estimate yourself?
Suddenly one day they asked, we never expected, one day they asked objective question. They asked, the flame color is red. What is the temperature of the flame? It was, so it's more than 1,500 over the flame color. But based on the flame color, they asked me what is the temperature of the flame. What objective question came up? So suddenly something out of the list can come up. One or two questions. Okay?
Yes.
Can you see the can you see the Cambridge? Can you see the Cambridge?
Possibly.
Is the mark scheme itself, they say you can't. It's just for your reference, you can't see them. Okay? Of course, they'll put it under, you should know, because it's estimation question, checking your general knowledge. So if you don't know,
But then that's so specific, though. Like, okay, I understand, like, the higher the temperature, the higher along the color spectrum it goes. But then,
yeah, not in the syllabus, but they suddenly popped up in the question.
but then 1,500 Celsius is like a specific number.
Yeah, they give 1,500, they give 10,000, 20,000, a big separation,
Oh, now this is the smallest one.
100.
100?
So, 100. So, try to have some general knowledge, try to have watch lots of National Geographic, some scientific documents, hopefully one or two questions only, one or two. Okay? Out of 100 candidates going to sit for that particular question, maybe if it's objective, maybe lucky, maybe less than 10% got it.
There's no objective paper, it's substrate anymore.
But it was asked in AS.
Oh.
Okay. Okay, guys, come on. Fill up this table. So finally, what are you going to tell? What are you going to ask? A comparison between the magnetic field and electric field. We done this earlier in the PowerPoint. Now what do you think? First one. So, three fields comparing. Gravitational field, magnetic field, electric. The gravitational field acts on mass object. Magnetic field. Alright. Magnetic field force acting on a moving charge particle. Okay. We just say charge particle. So the magnetic force acts on a moving charge particle. Okay. Or charge particle in motion. Okay. So the charge particle doesn't move. Magnetic force, capital general move, won't apply any force. If we go and touch the magnetic field line, there will be exert force. Okay. So force acts on moving charge particle in motion. Electric field acts on charge particle, regardless of its state of motion. Okay, whether it's moving or not moving, it's being force. Okay. First sequences. Right on, act on moving charge particle for magnetic field, act on charge particle regardless of state of motion. Two, direction of force is parallel to the field line. Magnetic field perpendicular to the field line. Okay. Electric field parallel. And the force is always parallel to the field. Okay. So gravity and electric almost lots of similarities. Magnetic is the one quite weird. That one?
The force is the charge particle in the state of motion.
Gravity's force is acting on a mass object regardless of the state of motion. Magnetic field? Only for a moving charge. Charge which is in motion experience force. Yeah. So electric field, same as the gravity, but replace the mass with charge.
So,
Yeah.
so just the question with the I and D, right? D is distance between the wires or length of the wires.
Distance means the two wires. The distance means if you have two wires like this distance.
So it can be any number.
Normally the wires up here, how far away one to another wire? 2 centimeters. Cannot be meter, few centimeters. Okay, so yeah, this is the first part of magnetic field. So we're done with this. So what you learned so far? So these are the things you learned.
Good morning.
So you know, very fast recap. So you need to know the three patterns: long wire, circular, solenoid. Then you have to know the BIL sin theta. Then you need to know the BQV sin theta. Sorry. Okay. Then you know this charged particle move in a circular path. This gives lots of problem for us. So therefore, it moves in a circle. Radius formula FP equals to FC. Then went to Hall voltage. Hall voltage, which direction is deflected, where the electric field, and so on. Okay. And the important formula, the D is the dimension, which is parallel to the magnetic field line. Okay. For the plate. Okay, then we talk about mass spectrometer, velocity selector, and finally these wires. Yeah? Okay. Okay, so 5 minutes as we go through one pass here. Okay, recall back all the knowledge you learned. So let's go one pass here. Okay, the first question. A charged particle may experience a force on in an electric field and magnetic field. State two differences the force experienced the two types of field.
One is parallel, one is perpendicular.
The force, what is parallel?
Electric in the electric field. Experience in the electric, a force experienced by a charged particle in an electric field is parallel.
Parallel to the
field line.
So the force in electric field is parallel to the field line. Parallel in magnetic field is perpendicular to the field line. One difference. Yeah. Another one difference.
The force experienced by the charged particle in a magnetic field is regardless of the motion.
Yeah. So force, the moving charged particle does not experience. Charge in rest does not experience force in
Magnetic field.
in magnetic field.
Like
Like it experience force in electric. Okay. The charge in rest only experience force in electric field, but not in magnetic. Yeah. Okay.
what?
So two differences.
What?
Okay. The charge in rest only experience force in electric. Okay, next. So proton get into this region and arc of a circle. Don't treat this as parabolic path, it's arc of a circle. Okay. Goes down. Okay, they give the speed is 4.5 times 10 power 6. Okay. So the strength is 0.12 Tesla. Okay, so let's go to the question. Yeah. Question is, state the direction of the magnetic field. Which direction the magnetic field? Into the page, out of the page, to the right, upwards, downwards, out of the page, out of the page. Driving left hand. Out of the page. That PI. I is that PI. Current is to the right. From down. This time I check, is it positive charge or negative charge? Positive charge, same direction the current. PI. F is which direction?
Downwards.
Because downwards. So magnetic field is out of the page. Magnetic field is out of the page, climbing left hand rule. Okay, next. Calculate the radius of the path proton in the magnetic field. What is the radius taken by the path of this proton? Find the radius. So what radius of this collision? We make a circle. How much is the radius?
You have to draw it out.
BIL. BQV equals to MV squared over R. BIL for a conductor. BQV for a charged particle. So this is I think one on top, so another 3 marks down here. So of course magnetic force equals to the centripetal force. So BQV equals to MV squared over R. This is your V. This is also V. So the radius found to be what? MV over BQ. So you substitute all the information, should get the radius. Right? Okay. The key idea is start with FB equals to FC. Right? Oh yeah, okay, last one. Sorry, before we continue this, I don't want to go this. I have suddenly one question pops up in my mind. I thought of one to ask this. Okay, that day you did the experiment in your second semester with magnet, right? Put a wire, you let the current flow, you read the reading of the ring scale. You done this experiment? Second semester? Right? So you have a wire, there is a magnet at the side, you adjust the current, you get the reading of the ring scale, right?
No.
Okay. So you have the scale, okay? You have a magnet, right, at the side, okay? Okay, this question is sometimes confusing. Okay, let's say this is, okay, you have a conductor here. The conductor is the view from the side, okay? What the question? Okay. Okay, the question asked when the current is on, when the current, okay, this is the current, let's say, going into the page. Current is going into the page, into the page. So here the reading, when the current start to flow, this magnet, this is the magnet, these two are magnet, okay. So when the reading increases, found to be the reading increases. When the reading increases, find the polarity of the magnetic field. Is it to the right or to the left? So let's say the reading of the ring scale is increasing and the current is stopped. Get the polarity of this magnetic field. Which side is not? Where's the magnetic field directed? To the right?
Is it
To the left? Yeah. Current is into the pitch.
Into the field.
Current is into the pitch.
The
The reading is increasing. So the magnetic field is to the right. So why is it magnetic field should be to the right? D is to the right, current is to the page. Because you point the force downwards. Okay, so idea is force because you know you think it's force is downwards. So therefore magnetic field is to the right. But if the force is downwards,
What?
if the force is downwards,
Is it increasing or not?
that's the charge. The reading is increasing. That means the reading increasing because the magnet has been pushed where? Downwards. The force shown here is the force experienced by the magnet or the wire? The magnet. The magnet experiences force downwards. So the wire experiences force upwards. Why? Section, reaction, fact. Okay. When the magnet is pushed down, that means the wire experiences force upwards. So when you use Fleming left-hand rule, the force you point where? Upwards. Not downwards.
So
That's the charge.
what happens to the wire one is experiencing the downward view?
If the wire experience, if F equals to DIL, that force is which force? Force on a conductor or force on a magnet? F equals to DIL. The F is force acting on the conductor or the magnet? On the conductor. Okay? So here, the conductor force is upwards, then the magnet will push down.
Why is it upwards?
Because here I told you the reading is going up. If the reading here goes up, means the magnet is pushed down. So if the reading here increases, means the magnet is the one in contact with the waves, right? So the magnet will experience force where? Downwards, right? Then only you can increase the value. Right? So magnet going down means the wire experience force upwards. So when you use Fleming left-hand rule, FBI, so F must be pointing upwards. Okay? So reading increase, force upwards. Reading decrease, force downwards. Okay, let's shortcut. Remember that. Okay, so we stop here. Okay. So as homework as usual, so go and try to do the papers. So tomorrow practical we done C4. Let's say we do C4, C5. Let's say C5, right?
I like to see C4, but I don't know.
C5.
Maybe.
Okay, let's say we done C5. What we did last week? C4. Okay, let's say we done C4. So C5 going to be your homework. So tomorrow, today, spend 1 hour, complete the report. So tomorrow, we just spend 10 minutes to check the difference. Okay, so draw receivers, get all the things for the C5 value. C5, 10 minutes, then we go ahead with the design experiment. Okay. So C5 is your homework. C5 is your homework. Today is 1 hour. Okay, thanks. I think we're done with the C4, last one. It's okay, you do the C5 first, then we see.